recording. It's now recording. Um, yes. Happy Wednesday. Uh, course things. There's stuff due. Um, today's the last day for problem set 5. If you haven't already turned that in, please make sure you do so by midnight tonight. TA3 is open, has been open. It's due a week. It's due in, what is it? A week from today or something, I think. July 31st, whatever July 31st happens to be. Yeah, that's a week from today. Um, so make sure to take a look at that as well. This is your daily reminder that the leaderboard is a thing. So even if you've submitted it and gotten all the points, you want to sort of hyper optimize your code and make it run faster, you are welcome to do so. And there will likely be uh, something like 5% extra credit on the project for getting on this particular PA for getting top 10 in the leaderboard, and then an additional 5% for getting top 3. You could get a potential of up to 20% extra credit if you do the write-up and you get one of the top 3 times. Also to clarify, some of the submissions in here are me and the TAs. We do not have very good submissions in general, but top 10 will be computed excluding those. So yeah. Cool. Oh, the other thing, I got an email this morning about course evaluations. So apparently that's a thing. Ostensibly, you all got sent a course evaluation form on Monday. Take a look at that if you haven't already. I understand that a lot of classes offer extra credit for submitting a course evaluation or for like submitting proof of a course evaluation. I suppose I may as well do that. So um, I'll make an extra a thing on Brightspace where you can submit a screenshot of the sort of like confirmation thing that you get after you submit. I also understand that the version of the the evaluation form that was sent out on Monday probably did not have an option to get a confirmation page. But I think it's been updated. So if you did it then and you want to do extra credit, feel free to go through it again and just get the confirmation page screenshot thing and submit that. Um, yeah, cool, good stuff. Oh, problem set 6. I was working on writing it last night, and I realized that there's a bunch of stuff that I wanted to put on it um, that was kind of a little bit outside the scope of what we've talked about in the past week. So it is going to be entirely extra credit, which means if you're keeping track, there's 5 problem sets that are worth actual points, and a 6th one, which is entirely extra credit, which means each of the 5, so the problem sets are worth, I think, 30% of your total grade. So each of the 5 is going to be worth 6% of your total grade. And then this one is going to be worth 6% extra credit. I also worked through this last night and realized there's a potential of up to 15% extra credit on your final grade if you take all the extra credit opportunities, which is great. I think that's great. I think that's good. Um, so um, there are uh, we are working on transferring grades into Brightspace. Um, and dealing with regrade requests and stuff like that. So I do apologize. We are a little bit behind on that. Um, but those will get caught up soon. Uh, and again, sorry, speaking of regrade requests, exam, the deadline to submit a regrade request for that is 2 days, the day after tomorrow, so Friday. Um, if you feel something's been graded unfairly. After that, exam grades will also be pushed into Brightspace. Okay, cool. Oh, I made a write up uh, a write up assignment in Brightspace for Project 3. So if you want to submit a write up and get another 10%, up to another 10% extra credit, please feel free to do that. Any questions on course content before we talk about computer science? Excellent. Create a whiteboard. All right. We'll erase. There we go. I'll start with the ceremonial writing of the word graphs. Yeah, okay. Okay. So I was debating with myself last night about what I wanted to talk about today. And I was between talking about strongly connected components and Tarjan's algorithm and this sort of thing, and spanning trees. And I think what I landed on is that spanning trees are more important. Um, so we're going to talk about spanning trees, particular minimum or minimal spanning trees. But your problem set will hopefully have you think about Tarjan's algorithm on your own time. Okay. Oh, in particular, this does mean that we're done with shortest path algorithms and moving on from that. So I guess before I start talking about spanning trees, does anyone have any lingering questions about shortest path stuff? This includes Dijkstra's A star, uh, a simple breadth first search, Bellman-Ford, any of these sorts of things. Are there things from the past few lectures that you would like me to go over again? I guess we didn't really cover Bellman. Bellman-Ford is basically the like original thing where you sort of like revisit. Yeah, I guess I didn't call it Bellman-Ford, um, but maybe Dijkstra's and A star. Maybe I can say a few words about Bellman-Ford actually. Yeah. Okay. I mean, I guess I don't know. It's maybe not that interesting. Bellman-Ford is just the so if you remember our initial like dynamic program that we developed for finding paths visits every oh there we go visits every edge no matter what, and if so this is maybe like D1 or these are weights, right? So I'll call them W1, W2, and W3, and maybe I'll label these vertices A, B, and C. So the distance to A is 0, the distance to B is W2, the distance to C, if we do a depth first recursion, right? Or sorry, we do a breadth first recursion. So we start by visiting this edge and we say the distance to C is W3 or is W1. And then we move on and visit this edge. And if this happens to be smaller, then we update C and say it's W2 plus W3, right? So Bellman-Ford is just the original like update distances algorithm. Um, so obviously this is slower because you might end up having to revisit the same vertex multiple times, or you might have to like, yeah, you might have to relax a path more than once. Um, but it correctly accounts for negative edge weights, right? Because you explicitly compute the sum of those weights, right? So Dijkstra's, for example, if you've got something like this, where this is like 5, this is 6, and this is -3, the shortest path is via B because the total length is 6 minus 3 is 3, whereas this one is just 5. Dijkstra's will visit this first because it has an edge weight of 5, then it'll visit this edge, and then it'll refuse to visit this edge because it says, okay, I already know the distance to C. And so it'll compute the distance to C. It'll compute the minimum distance to C as 5 instead of -3. But Bellman-Ford will correctly account for this because it will, in fact, it'll visit this. It'll say, okay, C is 5. It'll visit this. It'll say, okay, B is 6. And then it'll visit this again and it'll relax C to go down to 3. Right. Of course, once it relaxes C, it has to then like propagate that information outwards. Right. So um, any descendants of C that we already computed distances to, we have to go ahead and enqueue those again and sort of figure out if the distance to C changes or if the distance to those descendants changes. So Bellman-Ford is slower in that sense, but it correctly accounts for negative edge weights. All the same like intuition and vibes and stuff like that from the past few days still apply. Does it make sense? Cool. Any other questions on that? Or on any other shortest path stuff? All right. Let's talk about spanning trees, spanning graph. Uh, I'm going to open with everyone's favorite part of every class, which is definitions. Um, okay, so we'll start with the definition of a spanning graph. So an edge-induced subgraph H of G is spanning if the vertices are the vertices of G. If the vertices of H are the vertices of G. Right. So for example, if I have a graph, something like that, the following is one possible spanning subgraph, right? So I could take this edge and maybe this edge, this edge, this edge, and this edge, right? Because the induced subgraph here is that, right? And you notice that the vertices are the same, right? So there's like this vertex shows up, that shows up, that shows up, that shows up, and that shows up. Does that definition make sense? The idea is spanning is like taking some subset of the edges so that all the vertices are still somehow covered. Okay. I'm gonna do this thing that you see a lot in math, which is just really funny. A spanning tree is a spanning graph that is a tree. Remember, a tree um, is a graph that has a unique path from from a chosen route to any other vertex, right? So in particular, this graph up here is not a spanning tree because uh, let's say we choose like this as the root. Um, there's two distinct paths from this vertex to this vertex, right? Another way of saying tree is maybe like a forest is a graph with a unique path with at most one path from between any two pair of vertices. Um, or between any pair of vertices, and then a tree is a forest which is connected. Um, but whatever, right? A spanning tree is a spanning graph. That's a tree. Okay, so we sometimes care about computing spanning trees, right? In particular, the let's consider a weighted version of this problem, right? So or maybe another definition. Uh, if G is a weighted graph, a weight of a spanning subgraph H is the um of the weights of the edges in H, right? So if I go back up here, and I assign weights to my edges, what is this? 1, 2, 3, 4, 5, 6, 7. I need 7 numbers. Someone shout out 7 numbers. I'm very bad at being a random number generator. 8, 6, 7. Okay. 8, 6, 7. I need 4 more. 5, 3. Okay. Yeah, very good. I was waiting for this. 5, 3, 0, 9. Very nice. Thank you. Okay. So if we look at the set of edges that we kept, right? We keep the 8, we keep the 7, we keep the 5, we keep the 3, and we keep the 0. Okay. So the weight of this spanning subgraph is 23. right? So we picked a set of edges that covers every vertex at least once, and we sum up all of their weights. Right? So as with anything, sometimes we care about finding a minimal. We care about like optimizing this, right? So um, a minimum spanning subgraph is a spanning subgraph with minimal weight, right? So in particular, this is like very obviously not, or this subgraph is very obviously not minimal with respect to the weight, right? Because I mean, morally, like we took this 8 edge when we could have taken this 6 edge and it would cover the same set of vertices, right? And we've got this like this spurious, we don't need this 5 edge here. We could get rid of this, right? So we could decrease the total weight by at least 7. I don't know, could we go further? Probably. But it's like, yeah, this is not minimal. Or this is not a minimum spanning graph. Um, let's talk about reasons why you might care about minimum spanning graphs. And then we can talk about an algorithm or two algorithms, right? So a handful of applications here. Some of these are sort of uh, very geometric, right? So one sort of idea is like maybe you have a graph that represents like a network of some sort, maybe like a transit network, right? So you've got like train stations as vertices, and you've got like uh, train lines as edges. Right? So maybe you've got something like this, and the maybe label each edge with a weight, and the weight represents like how expensive that line is to maintain, right? So maybe this is 100, maybe this is 300, maybe this is 50, maybe this is 160, maybe this is 12. This is like 350, and maybe this is 20. I don't know, right? So we've labeled a bunch of we've got a bunch of vertices, a bunch of edges. The edges have weights. And so one thing that you might want to do is say, okay, well, I want to keep all of the train stations as connected as they were before. Um, maybe, I don't know, it's probably better to think of these as like undirected graphs, right? Because you can have trains that run in both directions. Or I'll just draw arrows on both sides so that I don't have to erase things. There we go. Right. You might want to say something like, okay, I want all of the stations that were connected before to remain connected. I don't want to make it impossible to get from one point to another, but I also want to minimize the upkeep here, right? So for example, like this this line costs $300 to maintain. That's a lot. Whereas I could sort of do the same thing by just keeping these three around. And like if I just keep these three and I get rid of this one, then these two vertices still remain connected. Like these two stations just still remain connected by routing all the trains through that. But I don't have to pay for this line anymore, right? Here's another really expensive one that I can probably get rid of, right? And so in particular, I notice that like here, if all I keep are maybe um, this one, this one, this one, and this one. Everything still remains connected, right? But my upkeep goes from whatever the sum of all of these numbers are to whatever the sum of these smaller, fewer numbers are. Um, Practically, don't in reality we care about the stress on the network? Yeah, you're right. This is a contrived example. Um, actually, that's a great point. Um, in the sense, yeah. So okay, practically we do care about the stress on the network. Practically, we might not want a bunch of trains running through here. We might say, okay, it is actually better to open up this line just so that we can like get things flowing in a different way. And we will talk about that hopefully next week when we talk about uh, max flow and min cut algorithms. It's my personal rail network. I want max coverage, minimum maintenance. Yeah, there you go. So there are another class of algorithms or another sort of class of graph problems that explicitly deal with like the 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 flow along different edges, right? So you think about like a source vertex and a destination vertex, and you think about like pushing some kind of material through the graph. Um, in this example, the material is probably like trains per second or trains per hour or whatever. And then you can sort of think about optimizing the graph to or you can think about looking at like what the possible flow is. Your rail network has implemented min flow max cut. That's very funny. Um, we should have a memes channel. Anyway, so ignoring practical considerations like people getting annoyed that they have to go through three stations when they could have taken the direct line. Um, this is some place where you might care about a spanning tree. Another one that I Googled yesterday, I did not realize people do this, but this is pretty cool, is um sort of like clustering, right? So maybe you've got a bunch of points in in some kind of metric space, right? This doesn't have to be like Euclidean. This could just be, I mean, honestly, maybe a better way to say this is just directly frame this as a graph. You've got a bunch of things and you've got like similarity measures between some of them, right? And so, um, whatever, right? You've got some set of similarity measures between them. And you want to find a good way of like decomposing these into clusters, uh, right? So maybe these are like smaller numbers mean they're more similar. So maybe this is like a 2, maybe this is like a 10, maybe this is like a 6, maybe this is like a 5, 3, 12, 7, 1, 11, whatever. Oh, I don't like 11 because it looks too much like two edges. So we're going to call it 33. Okay. So you've got these, right? And maybe you want to do something like figure out a way to partition the set of vertices into clusters that are mostly similar within each other, but maybe not necessarily similar across the different clusters, right? So one way you can think about doing this is finding a spanning graph with minimum weight. So for example, we could take this, this, uh, this, this, um, and this, I think, right? Maybe I should. I'm trying to like run Kruskal's algorithm in my head to do this, but oh, and we need this awful edge. Yeah, okay. This gives us a minimal spanning graph or a minimum spanning graph, and then we can sort of like pick the biggest few edges to cut, right? So we turn this into like wait, this is a 2, this is a 5, 3, 1, 7, 33, right? So maybe we say, okay, I can disconnect this, um, and I can disconnect this, and I can disconnect this, right? Maybe I want 4 clusters, so I disconnect the 3 highest edges, or the 3 like highest weight edges, and so I end up with like, here's a cluster, here's a cluster, here's a cluster, this one's all by itself, and this one's all by itself, right? And this kind of models like if you were to try to embed these into some kind of metric space where these were actual distances, um, then you would expect these two vertices to be close together, and you would expect them to be quite far away from this one, which is why it sort of makes sense that they don't end up in the same cluster, right? Whereas like this one, and this one are all kind of like very close to each other, right? Like a distance of 1 and a distance of 3, right? So apparently people use this, or think about this, I guess. I don't know. Um, Obviously, if you've got points in a nice metric space like Euclidean space, then you can use something nicer like K-means clustering, but whatever. Um, maybe maybe these are maybe these are not like uh, maybe these aren't like the usual Euclidean norm. Maybe there's like a Hamming weight or something like that, right? You've got like a bunch of species that maybe you're a biologist, you've discovered a bunch of species, and these weights represent like the number of differences between a pair of species. You want to say, okay, I want to classify these into like genuses or something like that. What's a good set of genuses to use here? And so you sort of like do this, and you say, okay, I want 4 different genuses, and so I don't know, maybe this maybe makes sense to someone. Um, anyway, applications. Okay, so let's talk. Oh, attendance poll. Attendance polls are nice. Everyone loves attendance polls. The poll for today is I'm going to make a claim, and the poll for today is I want you to justify that claim for me. And actually, this is an important claim. So I am going to sort of spend a minute thinking about this and maybe letting you all think about this. So the claim that I want to make is that the minimum spanning graph is always a tree. Right? So if we look at our examples, um, here, obviously the graph that we started with was not a tree. But the spanning graph that we found takes these edges. This is a tree, right? If we go, this is our, yeah. If we look at this one, right? Oh wait, sorry, I was going to, okay, this graph is not a tree, but the minimum spanning graph that we found is a tree. This graph here is not a tree, but the minimum spanning graph we found is a tree, right? Um, this graph is not a tree, but if we were to find the minimum spanning graph, it would include this edge and it would remove, sorry, it would remove this edge, right? So the minimum spanning graph here would be something like, take the 6, what am I doing? 6, take the 7, take the 0, because I'm just gonna not write things. Take the 0 and take the 3, right? Yeah. Um, and this is at least a forest, right? And if we think of this as an undirected graph, as we are prone to do, this becomes a tree, right? So Maybe I'll augment this by saying undirected. So for starters, do people believe me on this? Like obviously I've given three examples where this is in fact the case, where the minimum graph is a tree. Um, as we know, examples are uh, sufficient for a proof if the weights are non-negative. Yes, thank you. Uh, if the weights are non-negative. So any sort of situation where our graph weights look like a metric, right? So we want these to be non-negative. So attendance poll. Justify this. Does anyone have thoughts on why this is the case? Like um on a justification for this, maybe? If that isn't true, you have multiple distinct paths going to a node, and so one of them won't be the minimum path. That's exactly it, right? So if you have a spanning graph, which is not a tree, then by definition there must be two distinct paths from then there must exist like some u and some v such that we've got two distinct paths, right? But we only need one path. So if we delete one of these paths, or if we delete an edge from one of these paths, then it will still span the entire graph, right? The subgraph will still span the entire graph because we like deleting an edge from one of these paths won't disconnect U and V. So as long as the edge weight that we delete is positive or non-zero, sorry, non-negative, it will make the total weight of the spanning graph smaller. So that means the original one couldn't have been minimal. Great. Okay, so that's the answer. Write it up. Um, this is good though, because it means that when we say minimum spanning graph, really what we mean is minimum spanning tree. Right. So in particular, we can restrict our attention to just trees, right? We don't have to like this makes the search process or the search procedure a little bit easier. In fact, it enables like reframing this problem from spanning graph to spanning tree um, enables us to think about two very nice greedy algorithms for computing this. Are people here mostly familiar with like the vibes of greedy algorithms, or should I talk about this a little bit more before I describe the algorithms themselves? Talk about, okay, perfect. Yeah. Okay. So in general, um, a greedy algorithm Um, the morally, the idea of a greedy algorithm is you always take what looks like the locally best step, right? So, for example, if you were to try to like greedily find a path along the graph, you would always take like the you would always extend your path by the edge of minimum weight, right? If you were looking for shortest path, right? Depending on how you frame this might not actually return the optimal result because you might miss, like you might sort of take something like 1, 3, 2, 1, right? A greedy algorithm that tries to go from this vertex to this vertex would start by taking 1 because 1 is smaller than 2. Then it would take this 3, then it would take this 1, and so it would find a path of length 5. Whereas there exists a path of length 3 if we made this sort of suboptimal decision earlier, right? So often a greedy algorithm does not produce the optimal result. In some cases it does. Um, I'm going to erase this. More precisely, the steps to a greedy approach. Um, we start with some. So okay, I guess um, the idea of a greedy. I mean, a greedy algorithm makes sense for an optimization problem somehow, right? So we want to find. Uh, maybe I keep this up. Okay, so we say the problem is find S. S is a solution such that some predicate holds on S and some weight of S is minimal or maximal among all S, satisfying the predicate P, right? So in the case of path finding, find S. S is a path such that the predicate is the path starts and ends at the appropriate vertices, and that it is in fact a correct path. And the weight that we care about here is like the total weight along the path, right? Or the total distance of the path, right? So you can, so when you've got a problem that looks like find some solution that satisfies some constraint and is minimal or maximal with respect to some objective function, the greedy approach is we start with an initial, often it'll make sense to call this empty solution that satisfies the predicate. Um, and then at each step, find the minimal weight thing to add to S uh, such that P of S still folds, and then when you're done, you're done. This is a bit cheeky, but like when there's nothing else that you can add, then you're done, right? So you break, like, this is a while loop. You break out of the while loop, or when you break out of the while loop, you return the final S that you ended up with as your solution, right? So again, the idea is you start somewhere, and then at every step you just take what looks like the best possible step in that moment, right? And often this will not give you an optimal solution. Sometimes it will. The greedy algorithms are often not optimal, but sometimes they are. Now, mostly for the purposes of satisfying a bet that I made, I am going to like, sometimes they are, turns out to be a very interesting thing, right? Because in particular, it's very possible to know whether a greedy algorithm is going to be optimal or not, and that is uh, if the problem. So yeah, if the problem can be framed, or maybe if the problem forms a particular mathematical structure called a matroid, then the greedy algorithm is going to be optimal. Okay, I will talk about matroids maybe next week if there's time. Sort of after we've covered all of the stuff that you have to care about on the exam. Matroids are not going to show up on the exam. Um, I think they're cool. I think they're very it's weird how many places they show up. So I think they're cool. But in particular, uh, you can sort of show that this idea of like spanning trees um, gives you a matroid, or gives rise to a particular matroid, right? So we can look at a greedy approach. And it turns out that there's two ways to do this, right? Um, so I'll start by, actually, maybe okay. So minimum spanning tree algorithms. The two that we're going to talk about are called Prim's algorithm and Kruskal's algorithm. Okay, both of these are greedy. The difference is how they represent the solution set, right? So let's think about our sort of our components here, right? So we need a description of our solution set, we need a predicate, and we need a weight, right? So um, I'll describe the layouts here, and then we'll go into detail about what these algorithms actually look like, right? So maybe for prims, um, the solution is the set of vertices in a subgraph. Um, the weight is obviously the weight of edges, and the predicate. This is really what makes this work, right? Um, we know for a fact that any minimum spanning graph has to be a tree. So the predicate is that the thing is a tree. So we sort of make sure that it's a tree at every step. Kruskal's, for works exactly the same way, except S is now the set of edges. Right? So, um, yeah, this is sort of overview of these two algorithms. Um, More specifically, Prim's algorithm. We start our initial solution is just a single vertex. Arbitrarily, right? Arbitrary vertex. And then while while our graph isn't spanning, right? So while we still have more work to do, while the graph that we have isn't spanning, add um, the vertex with minimum distance from the graph, right? And then we're done. So maybe if I um, go back to the graph that I had before, what did it look like? Yeah, this one. Okay, so you've got the triangle and then you've got a nice commutative square with it. Okay, okay. I'm gonna redraw it here. Um, so we've got here's our graph, right? And we filled in these edge weights as five, as 8, 6, 7, what was it? 5, 3. I'm not gonna say 0. I'm gonna say 1, 9, just because I want these edge weight. Like I want non-negative. I want non-zero. I want positive edge weights. Um, but here's a graph. If we run Prim's algorithm, right? Maybe I'll start with A, B, C, D, E. I'll give these vertices names. Somebody shout out a random vertex to start with. It doesn't matter what we choose. I mean, it matters in the sense that it might give us a different graph to end with, but yeah, B. Okay, perfect. So let's start with B. Oh, also, I want to make this undirected for reasons that I will explain in a moment. Okay, so I start with B, right? Now, of the vertices that I haven't visited, so A, C, E, and D, right? The distance of A from our graph is 8. The distance, or sorry, yeah, the distance of C is 7. The distance of E is 3. The distance of D is 1, right? Which vertex do we add? Which vertex is closest to the graph right now? You can shout it out. It's going to be D, right? Because D has a distance of 1, so it's the closest, right? So we want to pick the edge with minimum weight that's not gonna like that's gonna keep this a tree. right? So we want to pick a vertex to add that hasn't been added to the set of like we want to pick a vertex that we haven't covered yet, such that the edge by which we introduce it has minimal weight, right? So our options are sort of this, and this, and of these 1, 3, 7, and 8, of these one has the smallest weight, right? So we pick one. Now our options are this, and this, because we've already introduced this, but now like we've already introduced the one, but now we have this one, right? So we've got the 8, the 7, and the 9. Oh, and the 3, right? So the smallest one here is the 3. We'll take that. Right. Now my graph looks like that, right? So my options are this one, this one, this one, or this one. I don't need to look at this edge anymore. In fact, I can't look at this edge anymore, the 9, because it's between two vertices that I've already visited or that I've already added, right? So if I were to add this edge, my graph would no longer be a tree. So in particular, adding this edge would break my invariant. It would make my solution no longer satisfy my predicate, right? So I can't add this edge, right? So I think about which vertex I can add next. I've got my options are A and C. The distance for C is was it like 5 here? The distance for A is uh 8, right? So I'll pick the closer one, which is C, and I'll add it via this horizontal edge. And then finally, I've got A, and I'll add A via this edge of size 6, right? So I've got 1, 3, 5, 6. Cool. And I've covered every vertex. Yeah, I feel good about that. Cool. Okay. So this is Prim's algorithm, right? We start with a source vertex, and then we add like we sort of and while we haven't covered all the vertices, we find which vertex we can add that will increase the total weight by the least amount, and then we add that vertex, and then we find the next vertex that will increase the weight by the that'll increase the total weight by the smallest amount and not introduce a cycle. So like actually, you don't have to worry about not introducing the cycle because you're just adding vertices that you haven't added yet, right? So we start by adding. So we start with B, then we add D, then we add what do we add next? We added E, then we added C, then we added A, right? And so by adding them in this order and sort of by adding these edges, we get we ensure by construction that the graph that we end up with is a tree, and it's going to be minimal, right? Um, the proof of optimality here uh, is just showing that this problem is a matroid, and then showing that greedy algorithms are optimal for matroids, right? You can also prove it directly, but it amounts to the same thing. Um, I won't cover the proof right now. Anyway, Kruskal's algorithm I will talk about tomorrow. Oh, wait, I fully meant to make this announcement earlier. I'm canceling lecture tomorrow. I'll post this on Piazza. Um, so uh we'll pick up with Cruise Calls on Friday. Yeah. Have a good one. I'm gonna stop the recording.